Okay, so this is the last slide we were working on a couple of days ago. And just to remind you the context. The context is that we are interested in studying how the electromagnetic field of a plane wave is affected when it crosses a region which is not only filled up with plasma, but also with an external magnetic field, which is here in this figure is just B0, which for simplicity we took as parallel to K, to the wave vector, so to the direction of propagation of the wave. And so we've come up essentially, we studied how we solved the motion of the electrons, so by deriving the velocity, and we obtain how it scales with the electric field, with the resulting electric fields. Here, omega b is the cyclotron frequency associated with the external magnetic field. So in a very similar way to the previous case, which was the one we considered in the absence of any external magnetic field, we obtain the so-called conductivity of the plasma, which we call sigma. So something which tells us about when an electric field, so considering the plasma as a medium, so no more the logic passages to move from a plasma, from considering the plasma as a bunch of charges within vacuum as a medium with its own dielectric properties. Okay, and so following the same line of reasoning as in the case of no magnetic field, we obtain the plasma conductivity, which tells us the resulting current density J in response to a given electric field E. And okay, so this is just the plasma conductivity. So by comparing it with what we obtained in the absence of magnetic field, the novelty that you immediately spot is the presence of, well, not only of the cyclotron frequency associated with magnetic fields, which again, if there is no magnetic field, you end up with a special case of just, I don't know, omega b. But the very last observations I just wanted to make last time is that you immediately see that the minus plus sign distinguishes between the two cases. We are considering not a generic plane wave, but a plane wave, both circularly polarized modes. So where the upper sign, so in this case minus, stands for the right circularly polarized case, and the plus, so the bottom sign, just stands for the left circular or negative helicity, whatever you want to call it. So this immediately introduces a degree of asymmetry between the two circular polarization modes, and this is really important. And this is the core of the effect that we are gonna prove in a moment, which is the so-called Faraday rotation. So again, here I just copied the formula for the conductivity, and the very same thing that we exploited last time. So by exploiting the continuity equation, so the continuity equation about charges, so we know now J, by imposing that, you immediately obtain ρ. So I'm not gonna spend too much time on it, just it's the very same line of reasoning we saw last time. Essentially, the only thing that changes is the definition of the plasma conductivity. But apart from that, J is still equals sigma E, so the rest is just the same. So it's no wonder that we end up with the same expression, the same formula for ρ, where, again, the only thing that changes is sigma. So again, we can redefine the very same way the dielectric constant that we called epsilon as a function of sigma, in addition to omega, of course, where looking at the way sigma is defined, you immediately see that Indeed, we have to distinguish, as I said, between the two cases, between the two different circular polarization modes. So that's the reason why I put here as a subscript R and L, which stands for, of course, for right and left circular polarization. So we're right as the first, so the upper sign, and left is the bottom sign. So just by replacing the value of sigma, you end up with this guy here. And again, if you look at what shows up here, 4 pi n, where I remind you n is the number density of electrons, e squared over m. This guy is what we called omega p. Well, actually, it is omega p squared, which is the plasma frequency. So in the very same way, we just exploring what we already defined as the plasma frequency, and we saw the role of the plasma frequency. So frequencies, waves, just propagate through the medium. So in this case, through plasma, only provided that the corresponding frequency of the wave is greater than the plasma frequency. So it works as a high-pass filter. So whatever has a frequency below the plasma frequency doesn't get through. And again, you see the generalization of what we obtain in the absence of the magnetic field. In the absence of that, omega b, the cyclotron frequency is 0, so you get what we obtained in the previous case for the dielectric constant. So it was at the time omega p squared over omega squared. Here you see how this is affected. And in particular, again, you have to distinguish between the two cases. Yes, that's exactly what I just said about the two. And again, if you wonder where does the difference between the two circular polarization modes stem from, well, the answer is from an intuitive point of view. If you look at this figure, you immediately see that the Lorentz force, due to the presence of the external magnetic field, is the source of asymmetry between the two polarization modes. Let's see. So the consequence of all this. Well, as soon as we defined last time the electric constant, you automatically can define the corresponding refractive index, which we call n, not to be confused with the particle density. Okay. So in that case, nr, just to mean refractive index. In here, r and l have a different meaning. It's just the refractive index for the right and left polarization modes. So make sure you're not confused. So again, it's just a matter of seeing the new definition, the more general definition in this case, which is just the square root of this guy. Again, if you remember the refractive index in the absence of magnetic field, you see that this is just omega p squared over omega squared. So again, the novelty is here. So immediately understand that what is the consequence of this? Well, the consequence is not only that the electromagnetic wave propagate with a different velocity. In particular, both ends here are lower than 1. So it means that in both circular polarization modes cases, the velocity is slower than the speed of light in vacuum. But it's different between the two cases. In particular, what is the effect? Well, let's see, first of all, the consequence of this in terms of the phase velocity. Well, the phase velocity is omega over k. And so this means, as we saw the very last time, which is something which is greater than the speed of light, but this doesn't contradict, in any case, the special relativity, because we know that information travels essentially with the group velocity, not with the phase velocity. So this is the expression, just the formula, just by replacing the refractive index. What is interesting concerning one of the effects that is worth studying, and that's we're interested in this specific case, is that a different phase velocity between the two polarization modes. Well, the phase velocity is what tells you about how the phase evolves. And so a different phase velocity between the two modes, it means that while the wave is crossing, if you have a linear combination of both circular polarization modes, and we will see, for example, when this is the case, it means that the two circular polarized modes develop a phase shift, a relative phase shift, because they have different phase velocities. So while traveling the same path within the plasma, there's a shift in which I call here delta phi. So let's calculate now, just due to the fact that the corresponding effective indices are different. And so is the corresponding phase velocity, which is here. So let's calculate now what's the resulting shift in phase as a result of the different refractive index delta n. How can we do that? Well, first of all, let's calculate this delta n. In an interesting case, what is the interesting case? Well, in the case in which you are supposedly observing at a frequency which is much above, well above the plasma frequency. Otherwise, you wouldn't be observing anything at all because of the of course, the wave otherwise couldn't get through the plasma. And as a matter of fact, in the observations that I was mentioning, we've seen that for typical plasma densities, omega b is of the order of megahertz, typically, which means for a Gaussian field in Gauss units, so it can be even smaller. So it means that if you observe at a frequency which is not only much larger than the plasma frequency, but also much larger than the cyclotron frequency, it means that this quantity is negligible with respect to 1. So the refractive index in both cases is close to 1, but they are different. So let's calculate how different they are. So first of all, as I said, okay, the refractive index is very close to 1, because the correction is small. Now, you can exploit a simple trick. For example, you can, given that you are calculating the difference between two quantities which are very close to one another, you can approximate the difference as the differential, the corresponding differential. So in this case, you immediately see that NL is greater, as a matter of fact, than NR, just because in the case of NL, you have the plus here, so a greater denominator, which makes this guy smaller, but this, because of the minus sign, this is greater. So NL is greater than NR. And if you look at this, given that you can calculate its differential, essentially, given that delta n is a small quantity. And so this guy minus this guy is just delta n. 2n, you are calculating the differential. So 2n times the n would be, but we call just delta n. The important point is that delta n is something very small compared to 1. So if you were instead, on the other side, if you just calculate this guy straight away, so you take this guy with NL minus NR, so you immediately see that you work out the common denominator, of course. You end up with this guy here, which turns to be omega b, and omega and minus omega just vanish. So you end up with twice omega p squared, omega b, over here in the denominator, I neglected omega b squared, because for the very same reason I told you here. And on the other side, 2n, n is 1, is approximately 1. So you can just take 1 here, 2 vanish with 2 here. So we are left with delta n, omega p squared, omega b over omega cube. So again, something very small, but now you know how small it is. Why is this useful? Because I remind you, the ultimate goal we have is that to calculate the phase shift due to delta n. Well, the shift in the phase is connected with the difference in the corresponding wave number, delta k. Because why? Because the wave number is the guy which tells you about the spatial periodicity. Okay. So this relation, which is the connection between the wave number and the corresponding frequency or angular frequency, you see that as soon as you change n, there is a corresponding change in the wave number, just like that. So that's the line of reasoning. You change the refractive index, so the corresponding wave number changes, and as a matter of fact, so for the same path, you have a different phase. So that's the line of reasoning we are following. So indeed, if you remember the formula for a generic wave, for a generic harmonic wave, so the argument of the sine, cosine of the imaginary exponential, whatever you want, is just kx, if you consider x as the spatial component, minus omega t. So kx, or kl in this case, a change in k, when multiplied by the path, so in this case, a small path dl, and then we integrate, is the shift, is the overall shift, and you have to integrate across across the path of this traveled by the wave. So this is exactly delta phi. So the difference, you have two waves with a different wave number traveling along the same path. So the result is a difference in the phase, which we call delta phi. Here, sorry, here there's a typo. I will correct. Of course, the integration goes from 0 to L, where L is the total path traveled by the waves. Okay. So, well, let's just calculate now that we can express the difference in the wave number as a function of the difference in the refractive index. So omega over c, delta n. What is delta n? This is just a reminder of the result that we obtained in the previous slide. Okay, so delta n is omega p squared, omega b over omega cube. So if you replace in this here, you see that you have an omega over omega cube. So you have 1 over omega squared. 1 over c is here, 1 over c. And then look, instead of putting omega p squared, so the plasma frequency square, I just put the definition of the plasma frequency, which is here among brackets, 4 pi n e squared over m. This is, okay, omega p. This is omega p, so the plasma frequency should be over 2 pi, the very same 2 pi. And times what? Times the cyclotron frequency. Again, I wrote explicitly what the cyclotron frequency is. You will immediately notice that here I put B parallel. Why? What is that? Well, this B is the external magnetic field that we took as a magnetic field which is completely parallel to the direction of propagation. Here, what I put here is a generalization, in the sense that here I consider the possibility that the external magnetic field is not necessarily parallel to K, so to the direction of propagation. But in general, it will have a component, a parallel component, which is indeed what is relevant. Because if we get back to the equation of motion, so to the second Newton's law applied to the electron, indeed, when you project the equation on the plane, which is perpendicular to the direction of propagation, because of the way Lorentz force works, you immediately see that what comes into play is just the parallel component of the magnetic field, which in that case we took as just the only one, the only component, because we took the parallel, we took the magnetic field as parallel. So this is a generalization. This means, okay, guys, even in the more general case of a magnetic field, which is not necessarily parallel, what comes into play here is its parallel component. Mind that B parallel can be either positive or negative. Why? Here is meant to be positive in the sense that the projection of the magnetic field onto the direction of propagation is positive when, of course, it's directed in the forward direction, not in the backward. But, and this is important because, again, it gets back to the Lorentz force. In the case of an antiparallel, or where the parallel component of P is just directed backward with respect to the line of, to the direction of propagation of the wave, of course, you have a minus sign, which comes into play in the equation of motion of the electrons. So this B parallel is indeed sensitive. It's not just the projection, it's the projection with its own sign. So it makes a difference on whether this projection is directed forward or backward. Okay, so this is something worth keeping in mind. So apart from that, I just put all the just the definition of the two plasma and cyclotron frequencies. Yes, that's exactly what I already told you. So let's rearrange. We bring all the constants out of the integral, so in particular 4 pi. N is, I remind you, not to be confused with this N. It can be a little bit confusing. You have to pay attention. I'm sorry for that, but that's the notation that is usually adopted. And I just, oh, by the way, I'm just following the treatment by Rybicki and Lightman in this part. But essentially, you can find it in many other textbooks that I listed in the references. So here, of course, if you are in control of things, there's no way you can get confused. You know that N in this case is what you have in the plasma frequency. So it can only be the number density of electrons. So you are integrating along the path, so along the line of sight traveled by the wave. So there's no way that in general you can take N out of the integral for the very same reason that we saw when we obtained the dispersion measure. So in general, N can vary. So it just has to be here. The same applies to the magnetic field. The magnetic field in general will depend on whether the region filled up with plasma has magnetic field, and the wave at some point just exits, comes out of this region, so then you have no more B. So B in general will be a function of the point along the path traveled by the wave. So again, this is something that you cannot take out of the integral. The rest are just constants. You see 4 pi, m squared, c squared, e cubed, all constant. Omega, well, omega in general, it's not constant, but for a fixed wave along the path, of course, the frequency is the same. So again, in this case, you can just take it out. So you see, this in this way, you immediately see that the shift between the two waves, so the left and the right circularly polarized waves, develop a relative shift, which is what we call delta phi. Why is this interesting? Which depends on, not only on the constant, not only on the frequency of the wave you are considering, but also on the content, on the integral content of both plasma density and the parallel component of the magnetic field. I'll get back to it in a moment, but what is relevant, and particularly what can be measured, is, for example, if you consider a wave which is not circularly polarized, but which is, for example, linearly polarized. And I'm going to prove you in a moment that, which is essentially the essence of what we call Faraday rotation, that when a linearly polarized wave enters a region, crosses a region with both plasma and magnetic field, the net result is that the wave will still be linearly polarized. Well, then I'll make some comments that may affect this, what I'm saying. But in general, the linear polarization will be still linear polarization, but the plane along which you have the linear polarization, so the plane along which the electric field is oscillating, will be rotated by an amount which is delta phi half, where delta phi is the guy we just called calculated. Why is this the case? Well, this is the reason why we studied so far the circular polarized waves instead of the linear. Because if you remember what we commented when we were talking about polarization, so a couple of months ago, more or less, there's something that I told you. You can look at a linearly polarized wave as the linear combination, the superposition of both epsilon plus and epsilon minus waves. So you can think of, and this is what this kind of sum in terms of in a sketched in this figure here is telling you. So if you take one positive helicity wave and one left helicity wave, and you add up, so you sum up. So you sum the resulting electric field, in which in this case is rotating counterclockwise, and this way is rotating clockwise. Well, you see that it's just immediate to see that the resulting electric field will be oscillating all the time up and down. So it's a linear polarization. Okay, so a linearly polarized wave can be seen as the superposition of two opposite circularly polarized waves. That's where we can exploit the results about circular polarization. So what happens when this wave exits or has just crossed some along a given path of length L, a region of plasma with N and B? Well, there's a shift which we call delta phi. So it's a relative shift. So it means that when the electric field for the right polarized wave will be again in this position, the left polarized wave will be shifted by a delta phi, which is exactly phi L minus phi R. So the left polarized wave will precede the right one by a delta phi. Now, of course, you have the superposition of those waves. So if you add up this electric field plus the electric field, what you get is just something lying at a half angle between these two angles. So the result is this of the sum is just this guy here. So if you consider the plane, so in this case the plane is just projected and which appears just as a line. So the direction of polarization prior to crossing the plasma and in the end after having crossed the plasma, you see as a net result that the direction of linear polarization has rotated by what we call delta theta, which is nothing but delta phi over 2. You see? Now from this drawing, it should be immediate. So the result is that, as I said, this is called Faraday rotation. So rotation, what is rotating? Well, the plane which describes the linear polarization. It goes without saying that if you're not lucky, or just put it the way you want, but if the wave you're dealing with has no intrinsic linear polarization, where there's no way you can measure this effect. Okay, so the ingredient which is required to weigh, to measure, to observe this effect, to measure, so you can speak of Faraday rotation only when, as a matter of fact, you are considering electromagnetic waves which are naturally, intrinsically, linearly polarized, because in that case you can measure the direction of the polarization, of the linear polarization, so you can measure as a correspondingly the shift. But the shift with respect to what? Well, you see, look at here. So this is the amount of the shift, well, over 2. Now we know that. What you measure is delta theta, not delta, so as a matter of fact, delta phi as well. You see that there is a wavelength dependence. So if you manage to observe the same wave at different wavelengths, you see that delta phi is a function of the wavelength. So you measure delta phi, you don't know it in principle, what is the direction of polarization of the wave prior to crossing the plasma. There's no way you can go, you can move up to there. But you measure essentially, as a matter of fact, the shift as a function of wavelength. In that case, you can reconstruct the relative, because you compare the shift, the phase shift between different frequencies. So, having clarified this effect, and having clarified that what you measure in the case of linearly polarized waves is delta theta, so a rotation of the linear polarization plane, which is this guy here, this guy over 2. I just copied and just divided by 2. Okay, here I simply expressed, instead of omega, 2 pi nu, so you gain an extra factor of 4 pi squared in the denominator, so this way. And here you see, here you have a lot of I've reminded you, we've been considering electrons. So E is, a matter of fact, the electron's charge, as well as m is its mass. So these are all constants. So you can just explain, and then here, for example, you can express, instead of nu, the frequency as c over lambda. So c lambda in the numerator. This is more convenient. This is more customary in the case of the Faraday rotation to use lambda instead of nu. So as a matter of fact, all bunch of constants, which if you calculate in the Gaussian system, for example, and you just leave lambda, so the wavelength expressed this way. So you see 1 over nu squared is equivalent to lambda squared. So 81.2 lambda squared, and then you have this guy here. And the result is in radians, provided that you express the wavelength in centimeter, the number density of plasma in a particle per cubic centimeter, the magnetic field in Gauss unit, and the path along which you integrate in parsec. If you manage to express these quantities in these units, using this formula, you get the result in radians. Radians, because this is a shift, an angular shift. And you see that the shift so scales with lambda squared. So if you remember the definition of dispersion measure, in that case it was a temporal delay as a function of frequency. There was a precise scaling with frequency, which is essentially the same here. Here is proportional to lambda squared, so again, scaling with 1 over nu squared. So again, we have an effect which is measurable. In this case, it's not a temporal delay between different frequencies, but it's an angle, a rotation angle by which the linear polarized wave is being rotated. And you see that the amount of rotation depends, in addition to depending on frequency, or equivalently on wavelength, it depends on this guy here. Well, this guy here, in particular, this guy here times this coefficient, so delta theta over lambda squared, which is for a fixed direction, depends only on this integral here, is called rotation measure, and it's abbreviated as Rm. The rotation measure, so it's a measure essentially of this integral here. So it's an integral which measures the magnetic field, or better, the parallel component of the magnetic field of the region which is filled up with plasma, weighted by the plasma density itself. So is this combination here. So the greater, so if you consider a region with plasma and magnetic field, the higher the magnetic field, and the correspondingly higher will be the rotation measure, or equivalently, the higher the, so in general, the combination, the product of the plasma density and magnetic field, or the parallel component of the magnetic field. So how can I be sure to ascribe the possible rotation of the plane of the linear polarization due to this effect, due to the combination of plasma and magnetic field? Well, again, you have a precise signature, which is the dependence on frequency or on wavelength. So again, if you manage to measure, to study the angle of the polarization of the polarized wave as a function of lambda, if you measure the square dependence, so the square scaling, again, this is a signature. That's exactly the scaling that you would expect due to the effect that we are considering, so due to Faraday rotation. So again, this works as a way to test the origin of this. If there is no such square scaling with lambda, well, it means that the rotation has nothing to do with Faraday rotation, okay? So this is, in addition to be a signature of this effect, once you clarify this, of course, the ratio between delta theta and lambda square is constant. At that point, you combine your measure, and you can directly measure this integral, which is connected with the properties of the region which has been crossed by the wave. So again, studying how the linear polarization rotates as a function of frequency becomes a probe that you have to study, to probe, to investigate the content of both plasma and magnetic field along the line of sight. What you need in this case, you immediately see, you need a source of linearly polarized waves. If you have no linear polarization crossing the plasma region, well, how can you measure the rotation of what if there is no linear polarization? So that's an important ingredient that you need. And and the other important point is, once you have this kind of sources, well, curiously enough, you can also measure the direction of the magnetic field, not only its magnitude, or well, its magnitude projected on the line of sight, be parallel, but particularly, as I remarked when I introduced B parallel, I told you, okay, mind that B parallel is a component, so it can be either negative or positive. So it means that, you see, the rotation angle changes, whether it's pointed towards you, or where the magnetic field points towards you, or in the opposite direction. So you are sensitive also to that. And so, as a matter of fact, when we apply all this stuff to astrophysics, so in particular to radio observations of the sky, in particular to our galaxy, and also other extragalactic sources, are there indeed possible, as a matter of fact, in reality, are there sources which provide us with a linear polarization? The answer is yes. Luckily enough, we have plenty of these sources. In particular, for example, in our own galaxy, pulsars, so neutron stars, which with relatively strong magnetic fields, which are naturally capable of emitting linearly polarized radiation. And the beauty of this stuff is that when you manage to measure from the very same source, so from the very same line of sight, both the dispersion measure and the rotation measure, so of course the source has to be capable of emitting linearly polarized waves, you can estimate the magnetic field. How? Well, let's see. You see, this definition, this average parallel component of the magnetic field, is a kind of weighted average of what? Of the magnetic field, where the weight is given by the plasma density. And you immediately see that this is a very general formula when you want to calculate the average, the weighted average of something. So here the weight is the role of weight is provided by the plasma density, and the point that you're averaging out is the parallel component of the magnetic field. But if you remember what we just defined, this is essentially part of the numerical coefficient. This is just the rotation measure in the numerator, while in the denominator is indeed the dispersion measure. So indeed, by combining from the very same source both measures, you have a handle on estimating the parallel component. Of course, it's an average, where again, the average is weighted by the plasma density. In the region in which the plasma is more dense, of course, this is a stronger impact on the rotation measure. So that's the meaning of weighted. The galactic magnetic field, so the magnetic field that we have in our own galaxy, is very important for many different reasons in astrophysics, because, well, it affects several processes, as I wrote here, from star formation. Also, of course, if you are interested in studying cosmic rays as charged particles, so as soon as they move, they are inevitably affected by the presence of a magnetic field, as well as if you are interested in CMB studies, because it affects the polarization. Now you see how it can change if you want to measure the orientation of the polarization of the CMB. Well, the presence of the magnetic field, so all the waves that are crossing the galaxy up to some extent will be affected, and will be affected in a different way depending on the rotation measure, on the corresponding rotation measure for any given direction in the sky. So if you're not aware of that, if you cannot account for it, then you are not able to ascribe what is intrinsic to the radiation you want to study and what is merely due to the effect of crossing the plasma and magnetic field that we have in our own galaxy. And you can imagine that since we live within the galaxy, and you probably remember from the course with Professor Rosati on astrophysics, that essentially the solar system lies at about 8 kiloparsec away from the center of our own galaxy. So we are off center, but we are within the galaxy, of course. So depending on the direction at which you look, your line of sight will cross different regions with different amounts of plasma or magnetic field. So you have to be aware, you have to kind of map the magnetic field and plasma content along all the possible lines of sight if you want to know exactly how the galaxy with its own plasma and magnetic field content can affect the radiation coming from background. Okay. And yes, of course, there's also another point why it is important to study, to reconstruct, to map the galactic magnetic field, which is the fact that on kiloparsec scales, which is more or less the scale which defines, as I said, we are 8 kiloparsec away from the galactic center, which is so strongly suspected to play a role also in the dynamics of the galactic disk. So if you know if you can constrain the galactic magnetic field, then you can automatically better constrain the dynamics of the entire galactic galactic disk. So there are many, many different reasons why detailed knowledge of the magnetic field, which is entrained in our own galaxy, is very important. And indeed, the combination of Faraday rotation and dispersion measure clearly for as many possible directions as possible. So it's a kind of probe that allows you, and as a matter of fact, one of the best, if not the best way to map the galactic scale, the galactic magnetic field on large scale. If you want to map the galactic, the magnetic field on very small scale, well, in that case you have to figure out something a little bit different. But so this is very important just because of that. So as a matter of fact, you see now you have a handle to understand how, as a matter of fact, we managed to measure the galactic field, the galactic magnetic field, as well as also in other galaxies. This is a map of what I'm talking. Oh, by the way, just yesterday there was a great deal of talks and press release about the latest data released of Gaia, this mission which is capable of measuring with unprecedented accuracy the positions and velocities of all the stars with our own galaxy. So again, this is not directly connected with the magnetic field we are talking about, but as a matter of fact, yes, they combined to study the dynamics of the galaxy. So once you know very well the position and the velocities of all the stars, so you can measure parallaxes, so distances, as well as you can study the dynamics with much greater accuracy. Combined to that, so it's also equivalent, it's also in parallel important to have a precise knowledge of the magnetic field, okay? So this is the map of what? Well, this is in galactic coordinates. So it means that what you see here, this plane, is the galactic plane. Of course, the galactic plane, as seen from our point of view, and we lie on the galactic plane just off center, as I was telling you. This is a color-coded map. What is this? Well, the unit of measure here is not reported, but it's essentially radiant per square meter. I remind you that the rotation measure is delta theta over lambda square. So it's an angle over a length square. In this case, it is customary to measure in units of radians over meter square. And so this is just the value. And you see the colors. What is the color? Well, blue and red. Blue, it means that, so this is the map. So this is a rotation measure map. So it is a way of measuring that integral. So the magnetic field, okay, weighted by the plasma density. But in particular, the color, the two different colors that you see, and all the range in between. So the most extreme colors are blue and red. What are they? Well, blue, it means that the magnetic field that results, and that you measure from the rotation directly, is pointing towards you. So the parallel component is towards you. While the red case is the parallel component, which is opposite to the line of sight towards us. So it's pointing away from us. So the blue region, the magnetic field is pointing toward us. The red region is pointing away from us. And the galactic center, of course, is just here, the center. So you immediately see how complex the structure is. And the beauty is that, as I said, you can reconstruct exactly the direction of the magnetic field, not only the intensity, but also the direction. This is another map of the magnetic field as seen from a different point of view. This is the galactic plane as seen from an hypothetical observer which lies way above the galaxy. So it's a different point of view. So GC, well, they're not my initials, but stands for galactic plane center, galactic center, sorry. And the sun is here, the yellow circle here. So this is just in, you see both X and Y. You see that here the sun is more or less at 8 kiloparsec from the center, as I was telling you. So you see the same color coded. And here you also see, instead of the rotation measure, here you see directly the measure, the parallel component of the magnetic field in unit of microgauss. Beautiful. So blue means that the magnetic field, you see all the arrows. The magnetic field where you see the blue colors means that it's pointing the parallel component parallel to the line of sight, so towards the sun, is pointing towards us. Blue, like in this case, you see, like in this case, the magnetic field. And you see also the intensity as a matter of a few microgauss, a number which is worth remembering, which I was already telling you. The scale is between 3 and -3, but then it can be larger, as you see, it can be. And while the red points, the red regions, are instead the regions in which the parallel component, so when you project the direction of the magnetic field along the line of sight toward the sun, is directed away from us. So look at here, for example. You see all these arrows are pointing away from us. And indeed, that it means that the parallel component of the magnetic field is negative. So negative in that sense. So you see the structure is really pretty complicated. So you see how powerful the combining Faraday rotation measure and dispersion measure can be. Really powerful. You can study and you can appreciate how complex the galactic, not only the average intensity, but also the structure itself. So it's really a unique probe for the galactic magnetic field. And what else could I say here? Well, okay, here you just have all these dashed lines. These dashed circles are just regions at equal distance from the sun. So this is 6 kiloparsec, this is 8. You see that we are a little more than 8 kiloparsec away from the galactic center. So this is a very important, one of the very important ways why in astrophysics, particularly in the radio band, the magnetic field, the Faraday rotation is very important. So let's see now a related, closely related concept, which is Faraday depolarization. What is that? Well, if you suppose that the source of linear polarization, it's not just a point source, but is an extended source. So the source, it's not now the plasma region, which is crossed by the electromagnetic wave. We are thinking of the source itself of the electromagnetic waves, okay? So, and let's suppose it's not a point-like source, but the size of the source itself is not negligible. So it means that electromagnetic waves are created throughout the entire source. Well, you can imagine that if the source itself is filled up with plasma and magnetic field, well, the source has a double role, both as a source of electromagnetic waves, so electromagnetic waves, in particular linearly polarized electromagnetic wave, will be produced throughout in all regions of the source, but also the source itself works as a plasma with magnetic field, so it affects the electromagnetic wave created in other regions of the source itself. So it rotates also the plane. So if the source is extended enough that the resulting electromagnetic waves that come out of the source are the superposition of sources of waves which in principle should have, for example, the same direction, the same linearly polarized vector, but the ones that are created further away have been rotated much more. But if they have been rotated due to Faraday rotation by, for example, pi radians, so 180 degrees. Then when you combine the electric field, they just cancel out. So it means that the very same source, when the source is extended, is capable of suppressing the radiation. Just because of Faraday rotation itself, so internal to the source, the rotation, when the rotation becomes large enough, and when is this the case? Well, if you remember, the rotation scales with lambda squared. So I would expect that if I call L the size of the source, well, when this integral n b parallel L, which is a given number, multiplied by lambda squared and the corresponding coefficient, gives a delta theta, which is comparable with 180 degrees shift. It means that the resulting, the sum of all the integral of all the waves produced by the source throughout the volume of the source itself, instead of increasing the resulting electric field, they will tend to cancel out. And this effect depends on lambda, because delta theta does. So you immediately see that at some point, when you have a source of linearly polarized electromagnetic wave, which is extended, you should expect that the longer the wavelength, you look at it, and at some point, instead of seeing a rotation, you see a decrease in the electric field intensity. So you see a decrease in intensity because the source itself is depolarizing. Okay? So because the resulting electric fields, which sum up and which are the contributions of different regions within the source, have been rotated one with respect to the other because they travel different paths within the source. So if lambda is large enough, so if the frequency is small enough, then you see that when you observe the source at correspondingly lower frequencies or equivalently at longer wavelength, you see that a decrease of the radiation because electric fields tend to cancel out. So instead of observing an increase and a corresponding rotation of the polarization of the radiation, you see a decrease of the polarization itself. So it becomes unpolarized because the electric field, instead of adding up in phase, they just cancel out. And this is called Faraday depolarization. Because of the very same Faraday rotation effect, as a matter of fact, the resulting polarization is suppressed, or if not completely, but significantly suppressed. So it's depolarized. And this is telling you something about also, not only about the plasma density and the magnetic field within the source, but also about the size of the source itself. Of course, the more compact the source, the correspondingly less, the smaller the impact of the Faraday depolarization. So when you are interested, for example, in studying the magnetic field within our own galaxy, you don't want to have, ideally, you don't want to have to do with sources which are strongly affected by Faraday depolarization, because as a matter of fact, the radiation coming out of the source is already depolarized. So it's no more a very good source of linear polarization. So if you could choose, ideally, the ideal sources that you need to use to probe the magnetic field which lie in between you and the source, you would reject extended sources, because extended sources are those which are mostly affected by Faraday depolarization. And in this respect, pulsars are again ideal candidates, because pulsars are very compact objects, a few 10 kilometers. So are ideal sources to our aims, for our purposes, because they are strong sources of linear polarization and compact object. So they are they are affected by Faraday depolarization in a negligible way with respect to, for example, to galaxies, our galaxies or extragalactic sources, which are much larger, much more extended. So in that case, you have to consider the effect of Faraday depolarization. Okay, so the very same effect, Faraday rotation, can also works against uh, the the linear polarization of the source itself. So can depolarize. Okay, I hope this is clear. And yes, okay, this is just essentially a comment in which I already made. Yeah, there is an exception in which about pulsars. If you take pulsars, which are relatively young objects, which are still well within their supernova shells, so the shells of matter which has been expelled as a consequence of the supernova explosion, which is also what gave birth to the pulsar itself. In that case, it is possible to observe, if you keep observing and measuring the rotation measure of the radial electromagnetic waves that are coming out of the pulsar and which have to cross the supernova shells. So the pulsar is still within the region surrounded by the supernova shell. So it's inevitable that the radiation coming out of the pulsar has to cross the supernova shell. So it means that a region with plasma and magnetic field. So it means that, of course, there's a contribution to the rotation measure due to the supernova shell. And in this case, because of the evolution, of the temporal evolution of a typical month timescales, here I reported over several months, you can measure, you can appreciate, you can really measure the change in the rotation measures due to the change in the delta, in the integral, if you remember, and be parallel. So in that case, when the source, when the supernova shell can be extended enough, of course, that can be also a change in also the depolarization in that case. Some degree of depolarization can come into play. So summing up, the rotation measure is what you get due to the integral of the combination of plasma density and parallel component of the magnetic field from the source of electromagnetic waves up to us. What essentially the electromagnetic wave crosses along its path from the source up to us. In addition to that, you have the depolarization. So Faraday depolarization, which does depend on lambda, and which is something which is due to what happens within the source. So if you integrate the path, along the path within the source, well, the amount of the result of this integral is what then is a measure of the degree of depolarization. So that's why a compact source is affected in the very least way, because just the integral the integral is short, because the integral, the path across the source, if the source is compact, of course, is a small contribution. By the way, nevertheless, of course, this guy then is multiplied by lambda squared. So it's something that at some point, if the source is extended, you start measuring from a given lambda, from a minimum lambda up to, so from a maximum down to a maximum, below a maximum frequency. This is an example of what you observe. So this is a map of a famous galaxy. So a galaxy which is of course megaparsec away from us, and this is M51. You see the same in 4 different images. Well, here this is a composite image, in the sense that you see all these lines are the electric field um, measured in the radio bands that I'm going to comment. And superposed to that, you see the picture taken in the optical, just to let you appreciate the relation between the electric field that you measure in the radio band and the optical, so the structure of the galaxy as seen in the optical wavelength. But let's focus on these lines. So these lines are telling you the polarization direction of the electric field, and the length of the lines are telling you about the strength of the polarized light. You see 4 panels, so at different wavelengths, increasing wavelength. You see here 2.8 centimeter, 6.3, 18 centimeter, 20 centimeter. So let's have a look. You see here the structure, and that's also interesting for many aspects. And you see that here, if you immediately compare, for example, from 2.8 to 6.3, so you are increasing the wavelength. So you immediately see that the average length of all these lines get immediately shorter. Here you see they almost resemble dots rather than lines. Well, you clearly see that they're lines. So it means that the intensity of the polarized light here is significantly decreased. And what is that? Well, this is indeed the effect of depolarized Faraday depolarization, because the intensity has decreased. You are increasing lambda. So given that this is an extended source, is the entire galaxy, you are just summing up the entire galaxy. What is the result of all the sources across the line of sight across the galaxy? So as a matter of fact, by increasing the wavelength, the same effect of the same amount of depolarization increased by lambda squared. So as a matter of fact, the electric field sum up and tends to partially cancel each other. So that's why it's, in addition to the rotation, you see that also, you also see the rotation. The higher the lambda, and you can appreciate the shift of the lines, so the orientation. So the line which is telling you the orientation of the plane of the linear polarization also rotates. For example, you can compare from this region here and this region here. You see that the line have been rotated. And also there are regions, for example, here you see some region in which you have a linearly polarized wave, and here you have a dearth. Here is just a kind of hole, because here you have a strong depolarization. So the more so by increasing, so you should see both effects, the rotation of the plane as well as the decrease in the intensity because of the partial depolarization. So you clearly see that this effect does depend on the wavelength. The higher the wavelength, or correspondingly the lower the frequency, and that. So you can exploit this to measure also to constrain the extent of the source, the size of the source, combined with the magnetic field itself and the plasma density within the source. Okay, let's, and this is all for Faraday rotation and related effects, like, as I was saying, the depolarization. Let's see, so this is a kind of, we keep on our sort of review of what the effects of plasmas on radiation are. And one effect that is very popular and very famous, that you already knew about that and already mentioned it just in passing, is Cherenkov radiation. So what is that? Well, let's consider a medium in which now light is propagating. And in this case, you immediately see that if we consider the case, for example, of a charge which is moving uniformly, well, from what we've seen about the retarded potential, something that we already discussed quite a number of lectures ago. I told you, well, in the case of uniformly moving charges, you have no radiation field, so there's no radiation coming out. And in particular, can be also be seen in this way, because I already proved you, I told you that I proved you that in the case of a charge moving uniformly, the electric field, when you calculate with their target potentials the direction of the electric fields and magnetic fields, they keep pointing where the source lies at the very same time. So apparently with no retarded. This is a property of the uniform motion. The fact that, as a matter of fact, their charge is not radiating, in this case, is a proof that you are not violating special relativity. So there is no energy coming out associated, energy flux associated with it in this case, because otherwise you would have an instantaneous change of the electric field just pointing toward the source, which would apparently violate special relativity. But this is not the case, because in that case we already saw there is no, because of the scaling with distance, there is no associated pointing flux associated with the velocity field. You need a radiation field. There's an interesting case in which, if you consider a medium, well, in that case, it depends on how the phase velocity of light changes in that medium. So to better appreciate what happens, let's remind ourselves what linear Wigner potentials are. And here I just copied linear Wigner potential. So the retarded potential in the case of one single charged particle moving, okay? Well, I remind you beta, well, beta is just the velocity of the particle in units of speed of light, and n is the generic direction of the observer, and r is the distance. So let's consider if the case of a medium with a refractive index which is greater than 1. Well, in that case, the phase velocity of light is the c over n. So it means that it is smaller than the speed of light in vacuum. But in that case, it means that you have to consider the possibility, which is not possible in the vacuum, of a charge which is moving faster than the speed of light in this medium, given that the light travels with a velocity which is c over refractive index. But in the case, as I said, of a refractive index greater than 1, it means that the speed of light is decreased. So at some point, it means that in principle, it is possible to consider what happens in the presence of a charge which is moving faster than the speed of light in the medium. Well, let's consider the factor that shows up in both the denominator of both the scalar and the potential field, the vector field, the vector potential. So what I call here the denominator as k, the denominator, the factor which multiplies the distance r. Not k, sorry, kappa. This is a Greek kappa. 1 minus beta. Well, in this case, beta is v over c, but c, instead of taking c, the speed of light in vacuum, I should take the speed of c, the speed of light in the medium. So c over n. So given that c is the denominator, c over n, it means that the refractive index gets to the numerator. So as a matter of fact, this guy here in the presence within a medium with a refractive index nr, the denominator, the factor in the denominator is this guy here. But you see, now n is greater than 1. So it means that there is a value of theta which in principle make kappa vanish. And it's just straightforward. You can calculate, and this is just the value. Now, given that, so if beta is large enough, so in principle, beta times nr can be larger than 1. So there is a solution, because this guy is smaller than 1. So there is a perfect value for there is a precise value for theta, which make, as I said, the denominator vanish. But what happens? What is the consequences on the electromagnetic potentials that we have here? Well, you see that immediately that for that very direction, both potentials can vanish. So in principle, it means that even if the particle is moving uniformly for this very direction, there is no more the constraint above the scaling with distance of the potential. So in principle, it means that the potential can be arbitrarily large for that direction. So it means that, as a matter of fact, you can have radiation associated. You can have Poynting flux associated with that direction. And this, you see, it's a peculiarity of medium with a refractive index which is greater than 1, and in comparison with a sufficiently fast particles. So how fast? Well, V over C over N has to be greater than 1 in order to provide you with a solution for theta. So it means that the requirements are a medium with a refractive index greater than 1 and a particle which is moving faster than the speed of light in that medium. In that case, for a very specific direction, which is this theta here, you can have both potential diverge. So essentially, it means that the corresponding Poynting flux is no more negligible. But a Poynting flux which is no more negligible, it means that it carries radiation. So this is a special case in which, despite the fact of dealing with a uniformly moving particle, you have an associated Poynting flux, so radiation. So the particle can radiate. And this is called Cherenkov radiation. You can also consider that in this very case, given that these potentials, of course, have to be our retarded potentials, so you have to first, when you want to calculate their values of any generic point at any generic time, you have to calculate to solve the retarded time equation. But you see, when the particle is faster than the corresponding speed of light in that medium, for any possible position and time, you might have more than one solution. And so indeed, what does this mean? Well, it means that in given points, you have more than one solution. So it means that at any given point in space, at any given time, you have the potentials that you have there at that time are the results of different contribution from the same particles when the particle was at different times in different places. So they just can sum up. And this is exactly what happens here in the case when the particle is moving with a speed lower than the corresponding speed of light. So here you see all the wave fronts which do not overlap. Something which instead is no more the case when the particle V is greater than, so when 1 over beta nr is smaller than 1. So in that case, of course, the particle is moving fast enough that the different wave fronts emitted at different times, they do cross. So they sum up in some points. So the result is that for a special direction, which is θ1, which is theta, which is whose cosine is 1 over beta n r, which is this angle here, and I'll show you why. For this direction, you will see radiation coming out, propagating through these yellow arrows. Of course, this is a cone. You have to imagine a 3D stuff. This is a cone. Why is this the case? Well, let's have a look at the drawing. And this is called, by the way, Cherenkov cone. Because in the time the source travels from here to here, well, the velocity of the source is just beta c, okay? So beta c, it means that in a time t, within a time interval t, the travel path is this one, but in the very same time, the wave fronts are propagating with the speed of light in the medium, so the velocity, corresponding velocity is c over the refractive index times t. So immediately see that the cosine of theta is this guy over this guy. So so it is just 1 over beta n r, which is exactly this guy here, which is exactly 1, the factor, the angle at which the factor kappa that I'm mentioning, that appears in the denominator of both potential vanishes. So, and from a pictorial point of view, you can see what happens across this line. Across this line, you see that all the wavefronts just sum up. Here, the drawing is just I just drew just a few wavefronts to make the figure clear in a sense. But you have to imagine that you have a lot of them, particularly at high frequency. So you have a lot of wavefronts just corresponding to the maximum of the emission, which are just summing up along this line. And that's basically the figure corresponding, telling you why you have the superposition of the why, as a matter of fact, you have the in the retarded time equation, you have more solutions. So you have the superposition of different wavefronts. So they sum up, and given that they are moving faster than the speed of light in the medium, they behave like they move subsonically. So it's a shock wave essentially. Of course, there's nothing to do with a hydrodynamic shock. It's not an hydrodynamic shock here. We are not talking about the dynamics of the gas or whatever the medium is, but about, of course, it's an electromagnetic shock. Okay, and that's all for the Cherenkov radiation. Of course, there's a huge this is a huge topic. It is exploited, for example, one clear application. There's many applications whenever you study essentially relativistic particles moving in media, and so whenever they move in media in which for which the corresponding speed of light is lower than the velocity itself of the particle, you have Cherenkov radiation. So you can exploit Cherenkov radiation also. You see, depending on the angle, if you manage to measure the angle at which Cherenkov radiation is emitted, you also have a clue on how to measure the beta, once you know, of course, the refractive index of the medium. So it's a way also of measuring the velocity of the particle. And for example, a clear application of this to reveal these particles is, for example, when you consider energetic cosmic rays. Is very, very ultra relativistic particles which enters the atmosphere, and so they are traveling at a speed which is greater than the speed of light within the air. So they emit Cherenkov radiation, and a lot of optical telescopes which are very sensitive in collecting these flashes of light, very faint light. So-called Cherenkov telescopes, their goal is just to measure the Cherenkov light emitted by this relativistic particle just crossing the atmosphere. So the atmosphere works as a detector in a sense, as part of the detector. And okay, I can, if you want to know more about this, in my optional course on multi-messenger astrophysics, I will be devoting quite some time to how this effect is exploited to measure very energetic gamma rays in particular, because gamma rays, they give origin when they interact with the molecules in the air with two relativistic particles, electrons, and this is something that I already mentioned, by the way, when I was talking about pair productions. So you have these showers of particles, which you observe also through Cherenkov radiation. There's also another effect which is worth mentioning, which is the so-called raising effect. What is that? Well, that's the opposite case, in particular the case in which we are probably more interested in, so the case of plasma. We saw that the plasma is characterized by the refractive index which is below 1. So there's no way that the line of reasoning that we just applied in the case of Cherenkov radiation could work here. Because if you remember the factor kappa, 1 minus beta n the refractive index, n times cos theta. Well, if beta is multiplied by n, which is smaller than 1, there's no way you can end up with there is no angle for which kappa vanishes. So there's no, in this case, no way you can have um, um, emission of a radiation associated with the analog of Cherenkov radiation. But instead, if you consider the so-called relativistic beaming that you know very well, so the angle at which the cone around the velocity of the particle, which is emitting most of the radiation, in the assumption that the particle is emitting in its moving frame more or less uniformly, isotropically. Well, in that case, again, let's see the impact of a different speed of light in the medium, in this case in the plasma. Well, the phase velocity now, again, like before, is c over nr. So c, the denominator, so again, n just shows up here in the numerator. The beaming angle, the relativistic beaming angle, is, if you remember, is 1 over gamma, which becomes interesting when this angle becomes pretty small, because in that case it means that you have a lot of radiation just concentrated along a narrow cone. So let's see how this is affected in the presence of a cold plasma. So a medium for which whose corresponding refractive index is below 1. Well, look at here. If n is below 1, is smaller than 1, there's no way you can make this guy vanish or make very, very small, and so correspondingly you to have a very narrow cone. Why? Well, beta at maximum can be just 1. Beta is V over C. So if something which cannot be larger than 1 is multiplied by something which is already below 1, there's no way this guy can be small. Unless two cases. Well, unless the obvious case in which indeed the refractive index is smaller than 1, but it's very, very close to 1. And we already saw when we were talking about the plasma frequency and the generic frequency at which you observe can be very well the case. So essentially, okay, and the refractive index, although it is in principle smaller than 1, but it is very close to it. So again, you can consider beta, when beta is very, very close to 1, so when the particle is sufficiently relativistic, in any case, you can have a beaming angle which is pretty narrow, which is pretty small. So the relativistic beaming, you have most of the radiation emitted within a very narrow cone. So essentially, it's the same as usual. Why? Because essentially, indeed, the refractive index is smaller than 1, but as a matter of fact, not enough. Okay. The second case is more interesting, is instead when the refractive index of the plasma is significantly smaller than 1. So you cannot compensate with a sufficiently relativistic, with a ultra-relativistic enough particle. But in that case, let's see exactly how the beaming angle depends on frequency. Why it is? Because we should remind ourselves that the refractive index does itself depend on frequency. So this is just a reminder of the formula for the refractive index in the case of a plasma whose plasma frequency is omega p. So here is just shows up. So let's consider an extremely relativistic particle where beta is essentially close to 1. Okay, so that the departure from 1 of this product is mostly due to nr rather than to beta. Okay, so we can just beta approximate to 1. So you see, if I replace the refractive index of the plasma with here, you just immediately come up with this ratio. So you immediately see that indeed I can recover the case of a relativistic beaming, which is pretty strong, So pretty strong means that this angle is pretty small if I consider sufficiently high frequencies. So it means that, in particular, if I want this guy to be 1 over gamma, well, it means that provided that I take omega sufficiently larger, how much large? Well, greater than, in such a way that this ratio is smaller than 1 over gamma. Well, in that case, so much smaller than 1 over gamma means that omega has to be greater than gamma times omega p. In that case, well, the effect is that the beaming angle is indeed smaller, comparable, and much smaller than 1 over gamma. So a strong relativistic beaming, a strong beaming of the effect. So this requirement is telling me, well, even if the particle is moving within, the relativistic particle is moving, is radiating within plasma, well, you have a strong beaming, provided that you considering frequencies which are high enough. But on the other side, what this means is that if the frequency you are looking at is not sufficiently large, it means that you have no beaming. Why is this relevant? Let's think of synchrotron radiation. If you remember, the spectrum of synchrotron radiation, unlike the case of cyclotron radiation, synchrotron radiation, the peculiarity of synchrotron radiation is that of a continuum spectrum, where the continuum spectrum, so energy over a broad range of frequencies, is due to the relativistic beaming. Why? Because you remember that when you move from cyclotron radiation to synchrotron radiation, what changes is the beaming angle, which makes you see only a very narrow pulse and then nothing, and very narrow pulse. When the velocity of the electron in the very moment along its orbit around the magnetic field is pointing towards you, you only receive radiation only in the very short time interval in which the line of sight lies within the narrow beaming cone of the electron. But look at this case. If the frequency is not high enough, you have no more narrow cone. And you see here, if omega is not large enough, it means that this ratio is not so small. So it means that the cone within which the electron is radiating is no more narrow. So, but that means that the synchrotron radiation resembles more the case of cyclotron, because if the relativistic beaming is no more so effective, so if the cone is no more so narrow, it means that essentially you receive radiation from the electrons, which is just moving around the magnetic field lines. You see for a relatively long time interval. This looks like a cyclotron rather than synchrotron. So it means that the spectrum is no more continuum. So it means that if you go, in this case, if you look at the synchrotron spectrum of a relativistic particle moving within a plasma, and if you observe the spectrum at low frequency, at some point you do not have any more the beaming effect at play. So the spectrum is no more continuum. So you have a drop in the spectrum. So it means that if you remember the spectrum of a single particle, the synchrotron spectrum of a single particle, you have the peak around the critical frequency, and then the low frequency region looks like a particle. You remember the asymptotic behavior, like a power law with an index of 1/3. Well, this regime drops, as in the case of a medium, when the frequency is so slow, so that this ratio is no more negligible with respect to 1. In that case, you have no more beaming. But if you drop the beaming, all the the reason why the spectrum is continuum in the case of synchrotron radiation is no more valid. And so you have the um, so-called cutoff in the spectrum at low frequency. Essentially, at low frequency, in the case of a plasma, the spectrum is no more synchrotron because the relativistic beaming, which is the key effect, the key reason for the continuum nature of the synchrotron spectrum, doesn't hold anymore at low frequency. So you see that the beaming here, which is the key effect in synchrotron radiation to explain the spectrum, holds as long as you keep at sufficiently high frequency. Below a given frequency, you have no more beaming. No more beaming means no more synchrotron radiation, no more synchrotron radiation continuum. So you have a cutoff. So this cutoff, at which you only observe at low frequency, is a signature of a particle emitting synchrotron radiation within plasma. So below a given frequency, you have no more what you would observe in the absence of plasma. So you have the synchrotron, but below given frequency, the cutoff. This is the signature of the so-called Raising effect, which is important for people studying synchrotron radiation of particles which are propagating through a plasma. So this is also very important in the lab, for example. Okay, I think that this is enough for today. Next time, which means on Wednesday, next Wednesday, we'll keep on considering also other very important effects due to the propagation of electromagnetic waves in plasma. In particular, we will examine the effect of irregularities. So if you imagine that at some point the electromagnetic wave crosses a region in which you have kind of blobs of plasma with different refractive indices because different densities. So you have a medium which is a screen. So imagine a layer of plasma within which you have blobs with different densities. Well, different densities we already seen means different refractive index. So we'll see that there are effects connected with refraction and diffraction. So we will see beautiful things, and we will see why, for example, the reason why light can scintillate. So you see that the point-like sources like stars, as seen from our point of view, just fluctuate, scintillate, while extended sources like planets, they do not essentially. Okay, this is a topic that we will go through next time. Questions? And then we will make a fair example of fast radar burst, which is a very hot topic in current research. Okay, so I